Okay, so hello everyone. So this is a continuation of the last live lecture where we were talking about torsion, extension, and then inflation. So there was some portion which I could not cover in the lecture, and I said I will make a separate video. So here I am making or recording the video for everyone. So let me share the screen, and then we will talk about the the remaining portion. But before I start, there is one thing which we need to discuss is that in the previous lecture, there was a mistake in this expression. This dA is completely outside of this bracket, and what we had written in the last lecture was dA was only associated with the second term and not with the first term. So that was a mistake. I pointed it out in the class also. But yeah, I verified it and that was a mistake from my end. So I have now rectified it. So this mistake you should not make. Okay. Now, accordingly, this expression has also changed because this A has come into picture here, which was not there. But but the portion that I want to discuss and which I did not discuss is basically what happens if P equal to 0. So this is the portion that I want to discuss. And I will discuss it in this slide only without making a white slide as I always do. So you see, I can write that epsilon zz is equal to 1 by E sigma zz minus nu sigma rr minus nu sigma theta theta. Now if P is equal to 0, A and B and not this area A. So I was writing it as AA to avoid any confusion. Let me write it as AA. So not this area A, but the constant A that we derived in our last lecture, both A and B will go to 0. Because if you remember, let me go back and show you what was A and what was B. So yes, so this was A. So if P is equal to 0, A is equal to 0. And this is B. Again, if P is equal to 0, B is also equal to 0. And if both A and B are equal to 0, sigma theta theta is equal to 0. And sigma RR, which is this minus will become plus, sigma RR is also equal to 0. So going back, so when P is equal to 0, if P is equal to 0, that implies sigma RR is equal to sigma theta theta is equal to 0, which means I have is epsilon zz is equal to sigma zz by E, which implies that sigma zz is equal to E epsilon zz, and epsilon zz is nothing but epsilon C or epsilon from our last lecture, which is a constant. So it does not change with area. Epsilon C does not change with the coordinate system. It does not change. And not a coordinate system with a change in the point. So sigma zz is equal to E epsilon C. Okay, the E is missing here, I can see. So with that, let us come here. And what do we have? F is equal to double integration sigma zz. I will write it as E epsilon C dA. Now epsilon C is not a function of dA. E is not a function of dA. So it becomes E epsilon C A, which implies that epsilon C is equal to F by EA. So a very simple proof, as you can see, and this is your epsilon. Now this thing I already discussed in the last lecture, that EA is known as the stretching stiffness and GJ is known as the twisting stiffness. So what do we arrive? So there was another thing. You remember gamma theta z was omega by L times air R. So this is coming from gamma theta z is equal to 2 epsilon theta z and epsilon theta z is part of this strain tensor, which we derived in the first lecture of this torsion, where this term was, you remember, ur prime, this was ur by r, this was uz prime, this was 0, this was 0, 0, 0, and this was omega r by 2l. This was omega r by 2l. So this was derived. If you go back, you can find it. So this is the term. You multiply it by 2, you get your gamma theta z. And then tau theta z, since we're talking about linear elastic isotropic material, is equal to G, the shear modulus, times gamma theta z. So what can we say from this equation? From this equation, we can say that tau theta z increases with increase in R. So if I have this circle, you can see as I go outside, my tau theta z is increasing. So this is my tau theta z, this triangular form. And at the center where R is equal to 0, my tau theta z is going to be equal to 0. So as you go outside, so if I take this circular cross section, so inner radius and outer radius, so obviously nothing can be here. So from here, as you go outside, your shear stress is going to increase, right? So yeah, so this was the only portion that was remaining from our last lecture. So I will wrap it up now and stop here. So thank you, and we will meet again in the next lecture, which will be about the large deformation and large strain. Thank you.